Today we are diving into the world of prime factorization. Specifically, we will be expressing some numbers as products of their prime factors. Here in the exercise 1, the first question is express each number as a product of its prime factors. So we will be expressing some numbers as products of prime factors. Okay, alright. So prime factorization is all about breaking down a number into its prime factors. Prime factors are prime numbers that multiply together to give the original number. So we start by dividing the number by the smallest prime and keep going until we have breakdown completely. Here we have got 5 numbers to factorize today. Those are 140, 156 and 3825 and 5005 and 7429. Let's factorize 140. The smallest prime number is 2. So let's start by dividing 140 by 2. So when we divide 140 upon 2, we get 70. So the prime factorization method is on dividing 140 upon 2, we get 70. Now we have got 70, which is still divisible by 2. So let's divide again. When 70 is divided by 2, we get 35. Now we have 35, but 35 isn't divisible by 2. So we move to the next smallest prime number, which is 3. By this 35 isn't divisible by 3 either. So we try 5, the next prime number, that is 4. When 35 is divided by 5, we get 7. Now we have 7, and guess what? 7 is a prime number. So we are done. So the prime factorization of 140 is nothing but 2 multiplies 2 multiplies 5 multiplies 7, which is 2 power 2, and 5 multiplies 7. That's it. For second option, 156. When 156 is divided by 2, we get 78. Now we have 78. We can divide by 2 again. When 78 divided by 2, we get 39. Now we have 39, which isn't divisible by 2. So we move to the next prime, that is 3. Now when 39 is divided by 3, we get 13. 13 is a prime number. So we are done. Now the prime factorization of 156 is 2 multiplies 2 multiplies 3 multiplies 13, which can be written as 2 power 2 multiplies 3 multiplies 13. Now let's tackle the third number, which is 3825. 3825 is divided by 3, we get 1275. Next we divide 1275 by 3 again. Now we get 425. Now we have 425, and that's divisible by 5 only. When 425 is divided by 5, we get 85. Again we divide 85 by 5, we get 17, which is prime number. That's it. So the prime factorization of 3825 is 3 multiply 3 multiply 5 multiply 5 multiply 17, which is nothing but 3 power 2 multiplies 5 power 2 multiplies 17. Now we have the fourth number, that is, so when dividing 5005 by 5, we get 1001. Now we have 1001. Let's try dividing by 7. When dividing 1001 by 7, we get 143. Now we divide 143 by 11 because it's divisible by 11. So 143 is divided by 11, we get 13, which is prime number. So the prime factorization of 5005 is nothing but 5 multiply 7 multiply 11 multiply 13. So we are done. Finally, let's try the final number, that is 7429. This one's a little tricky, so we will check for divisibility by primes up to around 100. 7429 is an odd number, so not divisible by 2. It's not divisible by 3, 5 or 7 by applying divisibility rule, but it turns out that 7429 is divisible by 29. When 7429 is divided by 29, we get 257. So the prime factorization of 7429 is nothing but 29 multiplies 257. And here we have it, the prime factorization of 140, 156 and the remaining 3 numbers. Remember, the key to prime factorization is starting with the smallest primes and dividing until you are left with only prime numbers. It's a great skill for breaking down large numbers and understanding their structure. Now let's move to the next question. The question number 2, that is given that find the LCM and HCF of the following pairs of integers and verify that LCM into HCF equals product of the two numbers, though the two numbers are those numbers given here. So find the LCM and HCF of the following pairs of integers. So first of all, we have to find LCM and HCF of the given numbers. So let's get started. How to find the LCM and HCF of numbers given pair, and we will even verify the amazing relationship given here, LCM multiplies HCF, which is equals to product of the two numbers. The given numbers are first one 26 and 91. We use prime factorization to find LCM and HCF. For 26, we have the prime factorization, which is when 26 is divided by 2, we get 13. 13 is prime number. Similarly, when 91 is divided by 7, we get 13. That's it. So the prime factorization of 26 is nothing but 2 multiply 13. When 91, we have 7 multiplies 13. The common factor here is 13. So the HCF of both numbers 26 and 91 is nothing but 13. We got HCF of the number. Now we have to find LCM. So the LCM is nothing but least common multiple. Take the products of highest powers of all primes. Now we have LCM is, we have 2 multiplies 7 multiplies 13, which is nothing but 182. Now we have to verify the given HCF and LCM and their product. Now the HCF multiplies LCM equals product of two numbers, that is 26 and 91. Now the HCF is 13 multiplies LCM is 182 equals 26 multiplies 91. So 13 multiplies 182, we get 2366, and when 26 multiplies 91, we get 2366. So both are equal. We have done. Now we move to the next number, that is the next pair of numbers are 510 and 92. Now let's look at 510 and 92. The first step is prime factorization. The prime factorization of 510 is nothing but when 510 is divided by 2, we get 2 times of 2, 4, remaining 1. 2 times of 5, we get 10, remaining 1. 2 times of 5. Similarly, now the last digit is 5. When 255 divided by 3, we get 3 8 24, remaining 1, 3 5s. Now we divide 85 by 5, we get 5 1s, 5 7s, we get 17. Now the prime factorization of 92 is nothing but when 92 is divided by 2, we get 4s, 3s. 2 4s, 8, remaining 1, 2 6. Okay, 2 times of 6 we get 12. Now 2 times of 2 we get 4, 2 times of 3 we get 23. So the prime factor is done. Now we have to find HCF and LCM of both numbers. What is HCF? Here I am writing 5 tens. Prime factorization 2 multiplies 3 multiplies 5 multiplies 17. And for 92 we have 2 multiplies 23. Now the highest common factor of both 510 and 92 is nothing but only 2. Common is 2, so the HCF is 2. Where LCM, we have to take all primes. Those are 2 power 2 and 3 and 5 and 17 and 23. So multiplying 2 power 2, multiply 3, multiply 5, multiply 17, multiply 23, we get 23460. Now the verification we have to do here. LCM multiply HCF is equals to the product of two numbers. Those are 510 and 92. The LCM of both numbers is 23460. Multiplies HCF is nothing but 2, which is equals to 510 multiplies 92. When multiplying 23460 with 2, we get 46920. When multiplying 510, we get with 92, we get similarly 46920. Thus we have done work as homework. Great. Let's solve this using the prime factorization method to find the HCF and LCM of the given sets of numbers. The first set is 12, 15 and 21. Now the prime factorization method, we have to find the LCM and HCF by using these set of numbers by applying the prime factorization method. So we know the prime factorization method is we have to divide with smallest prime number. So when 12 is divided by 2, we get 6, and when 6 divided by 2, we get 3, and 3 is a prime number. Similarly for 15 is divided by 3, so 15 when 15 is divided by 3, we get 5, which is prime number. Similarly for 21 21 is divided by 3. 3 times of 7 we get 21, and 7 is a prime number. Now we have to find LCM and HCF of the set of the numbers. Now the HCF is the highest common factor. Look for the common prime factors for all three numbers, that is 12, 15 and 21. The common factor is only, first of all I will write the prime factorization for the set of numbers. For 12 we have 2 multiply 2 multiply 3. For 15 we have 3 multiply 5. For 21 we have 3 multiply 7. Now look for common factors, that prime factors in all three. The common factor is nothing but only 3. Okay, so the highest common factor is 3. Now we have to find LCM, which is the least common multiple. Take the highest powers of all prime factors. So the highest power is nothing but we can write it as 2 power 2 multiplies 3. So now the highest powers in 2 we have the maximum, which is 2 power 2. In 3 we have only 3. In 5 we have 5, and in 7 we have 7. So the LCM is nothing but the product of these numbers. We get 420. So the LCM of the set of given 12, 15 and 21 numbers is nothing but 420. Now we move to the next set of the numbers, that is 17, 23 and 29. Now we move to the first step, that is prime factorization. For 17 we have only 17 times 1. For 23 it is also a prime number, and which isn't divisible by any number, so it is a prime number. Similarly for 29, this number also isn't divisible by any number, so it is divisible by only 1 and itself, so it is also a prime number. Now for we find a HCF. HCF is, for all we have 23 multiply 1, 29 multiplies 1, so the common is only 1, so the HCF is 1. Now the LCM of this set of numbers is nothing but product of the numbers, which is 17 multiplies 23 multiplies 29. We get 11339. Now we move to the final set of numbers, which is homework. Here given the fourth question, that is given that HCF of 306, 657 equals 9. Find LCM of the given numbers. Here we will learn how to find the LCM of two numbers when the HCF is already given. Given that HCF of 306, 657 is equals to 9. So we have to find the LCM of the given numbers. Now what is HCF? HCF is nothing but 9. Now we have a relation, that is LCM multiplies HCF equals product of two numbers. So this is, so now what is the HCF? HCF is nothing but 9. So we will write here 9. So we don't know the LCM. So we have to find the LCM. Now the product of two numbers, the two numbers are nothing but 306 and 657. So the product is nothing but multiply. Now the both numbers are 306 and 657. Now the number 9 will be divided to the product of two numbers. So LCM equals 306 into 657 upon 9. Now when multiplying 306 into 657, we get 201042. Now which is divided by 9, we get 22338. So we got LCM. And there you have it, right? The LCM of 306 and 657 is nothing but 22338. Using just one simple formula, that is nothing but LCM into LCF equals product of two numbers. The question number 5 is given. Check whether 6 power n can end with the digit 0 for any natural number n. Hey, the question sounds simple, but it's a great brain teaser. Can the number 6 power n ever end with the digit 0 for any natural number n? Let's see. To answer this question, let's think about what it means for a number to end in 0. That means it must be divisible by 10, right? So 10 is nothing but 2 multiplies 5. Now, so if 6 power n is to end with a 0, it must be divisible by both 2 and 3. Now 6 power n means multiplying 6 by itself n times, that is n times, and 6 is nothing but 2 multiplies 3, right? So any power of 6 will always include lots of 2's and 3's. No problem with 2's. For 6 power n, we have for 6 power n, we have as the value of 6 is nothing but 2 multiplies 3 power n. Now we have a formula that is equal to AB power n equals A power n and B power n. Similarly, we can write for this 2 power n multiplies 3 power n. But where is the 5? Where is the 5? There is no factor of 5 in 6. And no matter how many times you multiply 6 by itself, you will never create a 5. Without a 5 in the factorization, there is no way 6 power n can be divisible by 10. And that means 6 power n can never end with a 0 for any natural number. So the answer is no. 6 power n will never end in 0. It can be end in 6, 8, 4 or 2, but never with a 0. Okay. Question number 6. Explain why the given number 7 multiplies 11 multiplies 13 plus 13 and 7 multiplies 6 multiplies 5 multiplies 4 multiplies 3 multiplies 2 multiplies 1 plus 5 are composite numbers. First, we have the number 7 multiplies 11 multiplies 13 plus 13. Notice something interesting here. All three numbers, that is 7, 11, 13, are prime numbers. And when you multiply them together, you get 7 multiplies 11, we get 77. And 77 multiplies with 13, we get 1014. Now the question is 1014 a composite number? Well, let's check if it has factors other than 1 and itself. Look, Look at this expression, which is 7 into 11 into 13 plus 13. That's the same as 13 of 7 multiplies 11 plus 1. Let's simplify inside the parentheses. That is 7 multiplies 11, we get 77 plus 1 multiplies 13. Now 13 multiplies 78 is 78 multiplies 13, we get 1014 as it is. That means 1014 is divisible by 13 and 78, which means it has factors other than 1 and itself, so it is composite number. So 1014 is composite number. Now we have a bigger number, that is 7 multiplies 6 multiplies 5 4 3 2 1 plus 5. Similarly, this is just a 7 factorial, written as 7 factorial, which is 5040. So we have the value of 7 factorial, which is nothing but 5040. So we are really doing, that is 5040 plus 5, we have 5045. Again, let's ask, is 5045 a composite number? Let's try factoring. Can we factor out 5? That is similarly as like this. Let's check. That is 5040 plus 5 is nothing but 5045, which is nothing but 5 multiplies of 1009. 045 has more than 2 factors. So 5045 is also a composite number. Now let's check, explain why the given two numbers are composite. Yes, the given numbers are composite numbers, we have proved, right? The composite numbers are nothing but we have any number, if we have any number whose factors are other than 1 or itself, then it is called composite number. So 1014 and 5045 are composite numbers. Here the question given number 7, that is, there is a circular path around a sports field. We have a circular path around a sports field. Sonia takes 18 minutes. Who? Sonia. To drive one round of the field. So the one round of the field, Sonia takes 18 minutes. While Ravi takes only 12 minutes for the same. It means Ravi takes 12 minutes. Suppose they both start at the same point and at the same time. Same point and at the same time, and go in the same direction. After how many minutes? We have to find the minutes. Will they meet again at the starting point? It means that Sonia and Ravi. A given all about a motion on a circular track, and it will test your understanding of LCM. Yes, so let's get into it. Now here the scenario is, there's a circular path around a sports field. Okay, this is a circular path. Sonia takes how many minutes? 18 minutes to complete one round. For one round, Ravi takes 12 minutes for one round to complete the same round. Okay, they both start at the same time and at same point, moving in the same direction. Now the question is, after how many minutes will they meet again at the starting point? To find when Sonia and Ravi will meet at the starting point again. We need to find the LCM of their round times, that is 18 and 12. So let's move to the prime factorization of 18. When divided by 2 we get 9, when divided by 3 we get 3. Okay. Similarly for 12, which is divided by 2 we get 6, when divided by 2 we get 3. So now we have to find the LCM of both numbers. So LCM for prime factorization of 18 is nothing but 2 multiplies 3 power 2. For 12, nothing but 2 power 2 multiplies 3. Now the LCM of both numbers are the highest and the product of highest common multiples. So in 2 we have 2 power 2, and in 3 we have 3 power 2. So 2 power 2 is nothing but 4, and 3 power 2 is nothing but 9, which is equals 36. So here the visual is Sonia and Ravi meeting again at the starting point on the track after 36 minutes. That means Sonia and Ravi will move both the bag at the starting point together after 36 minutes. Even though they run at different speeds, 36 minutes is when their paths sync